Okay, just to recap, your L1, L2 is your test 1, L3, L4 is test 2. We will start test 2 will be focused on rigid body equation only. Okay. So your test 10% happened last week. So another one in week 12 or week 13. Right? Assignment I will give on week 11. Yeah, maybe next week I give you. Your lab report submit lab week 11. Week 11. Right. Okay. Chapter 5 also is a very big chapter like chapter 1. So I put a line there just to differentiate just to differentiate from chapter that appeared in your module. Right. So this one is a 2 chapter. So I combine in one. So okay, these are the things we will study. So we go by one by one. So today we only look at how rigid body behave when there's a force. When there's a force. Now, the first motion we look at planar motion. Planar motion means you look at the paper, and this is a handphone, so rigid body. It will move on A4 paper only. It won't move up, won't move into the screen. So first one, planar motion means you look at one plane, XY, YZ. It's a 2-dimensional motion. First, translation. Translation is what you've seen on the screen here. Let's say this is rigid body. You have a 2 point. You take 2 point on the body, and this is before and after you join the line together. The pathway move in a straight line. This is a linear or rectilinear motion. This motion you learn in chapter 1. But now you are looking as a rigid body. Okay. Another one, you learn in chapter 1 also, curvilinear motion. But now the rigid body, you will see the whole body moving on the curve by looking at the 2 reference points on the body. So in chapter 1, 2, 3, 4, you look at only 1 point. But when you come into rigid body, you look at the whole object. So later we'll focus on CG point, center of gravity. Okay. So identify the 2 basic motion on translation. Translation, it move in a plane and in the line form. In the line form, when you connect the 2 points, it move in the line form. So same like chapter 1, you have a linear, a rectilinear motion with a straight line and a curved motion. So next is on the rotation. Just now is a translation. In translation, it moved from like what you see on the screen. Another one is rotation. You're now looking at a complete body. So complete body, you have a 3-dimensional movement now. So you won't see this one in chapter 1, 2, 3, 4. When you look at particle, particle is just a dot. So no matter how you spin it, it's still a dot. Right? So when you move into rigid body, you can see the whole body spin because of inertia. Right? So this is a rotation on the fixed axis. So this one, this line is an axis, so it rotates. Okay. Then it can combine the previous slide and this slide. It can combine rotation and translation together. Means it's move forward or move to the left or right plus rotation. So as you can see on the screen here, the blue line, the path line here. So it will move from left to right. Translation you can look as go up, go down, go left, go right. Then the rotation is mean it rotate the axis. So there's an axis of rotation. So here it moved to the right, but the axis of rotation make it turn the thing. This is, you've seen this one in your experiment. Experiment 2, the L1, L2, L3, the A1, 2, 3, right? That one. Okay. So you look at this diagram at the center, you have a one wheel here. Wheel defined by a radius. And you have an arm that connected to a piston that in your experiment, you turn the angle, right? You turn the angle, then you measure the L. This is the piston. This is the part of experiment that you do. Okay? So this motion, when you turn this wheel, clockwise or anti-clockwise, this piston will move only left or right. This motion is called rectilinear translation. This is the rectilinear translation. Then if this one, the second one, if there's a pin here, the pin here with the R radius here, and it rotates, in this case, anti-clockwise, when you turn the wheel anti-clockwise, this one also will turn anti-clockwise. So this arm here, when you connect these two bodies, when it rotates like that, okay, we look at these 2 points. When rigid body, you look at point. So these 2 points, when you rotate, you see my finger, how my finger works is like a wiper. So it moves in the collinear motion. This is rectilinear motion. This one, okay, this one, although this one round, here is collinear, but this one translates into rectilinear motion. Okay, so the concept still same. If you see rectilinear, you can split all the vector into x, y direction. If you see rectilinear, you can split into normal and tangent direction. Still the same. But now you only need to focus on how the body move. How the body move. Okay, we try to derive some equation. Don't worry, you've seen this one before in chapter 1, 2, 3, 4. Now we only look at the sum of the body. You have a primary reference plane with its x and y. And you have your translating coordinate, meaning you focus on the body. And you see the axis now, we label as x prime and y prime. You see the prime, the symbol comma there means the object is moving. The object is moving. So your solve question always from the primary or reference fixed point, looking at the moving object. On the object, you always fix 2 points when it comes to rigid body. In this case, you have fixed point A and B, A at the center, at the origin of the x prime and y prime axis, and 1 point B on the body of the rigid body. So previously, we also know that R to represent location or position. So if you're referring to position A from your fixed point, we use R sub A. And if you're referring to position of B on the rigid body, you use R sub B. Then you will see something R B slash A. It means location of B from A. Okay, position. You write R stroke B, it means position B respect to A. And this is a vector diagram. You see this one is vector diagram. So starting RA, continue with R stroke B, you get final destination. You're completing the vector by resultant vector, starting point, end point. This one become your resultant. So resultant means what? This one equal to this one plus this one. This is how you're completing the vector. Right? So this one also you learn in chapter 1 or chapter 2. Same concept. It's now the question from for chapter 5 will always ask you question about this one. What is the relative velocity or distance from one body, from one point to another point, or from one location to another location? Okay, so okay. So the differences of a question, chapter 5 onwards, you're focusing on the rigid body, again, rigid body. Velocity is still the same. You derive from position r. How you find velocity? You differentiate with time. So this one, r will become v. R position will become velocity b. Same if RA become VA, and RB stroke A will become D, RB stroke A divided by T. And if you look carefully on the diagram, this is time integral, time derivative. On the rigid body, on your body, like for example, the distance between your eyes and your eyes, and maybe find one location, your eyes and your mouth always same, right? You won't move. So if this one is your eye, this one is your mouth, RB stroke A, will it change over time? It will not change, right? This is a mathematical equation. RB stroke A means this distance, or not this distance. You differentiate with time, means no change. So this one you can cancel, become 0. Means the distance between your eyes and your mouth is do not change over time. So you can cancel it. It arrives at one equation, which means velocity of B was same as A. It's like your eyes and your mouth. If you move to the left or move forward, the velocity of your eyes and mouth will be the same. So you arrive at VA equal to VB. This equation only works for rigid body. It's a bit different if you look at particles. Okay, so acceleration still same. You take time derivative of your velocity. It become AB and AB and AA. Okay. So still same. We will took the same pace as chapter 1. We'll look at what is position, what is velocity, what is acceleration. Okay. Now, we look at rotation on the fixed plane here. We will start using from chapter 5 or not even in chapter 4, you start to use right-hand rules already, because when you study about momentum and impulse, you use right-hand rules, right? You steal the cross products, R cross F on right-hand rules. When you come to rigid body, let's look at this diagram. So this, let's say we have a very random body, and this is moving in the radius of R, and we pick one position P, right? So when this body rotates at a certain fixed axis here, right? So when it fix and you rotate and you fix at point P, when you see it from one location, you are seeing P actually circling the center. Right? It's like your eyes, and then you rotate your body. You're seeing your eyes actually moving in a circle. Okay, so in rigid body, the first parameter, not parameter, but the first motion we call angular motion. Right. So the rest you write here. So the rest you read, The rest you read. I want to highlight the important, So how in rigid body, how you measure the position? You are using R to represent position, Chapter 1, Chapter 2, Chapter 3, you use S. You S to represent position. But when it comes to rigid body, we start to use R to represent rigid body. Huh? And the angle, we use theta. So this is a plane, and there will be a reference rotation angle. Rotation angle. Right? So you will call angular position. And the displacement, we call it d theta. Right? D theta. Okay. Then you need to recall the relationship between radian and angle. In mathematics, previously you learned small changes of angle and the circumference of the circle and radius. You relate S equal to R theta. This one is in radian. When you study about circumference, a small cross section of a circle. So one revolution from chapter 5 onward, you'll see question give you the object will rotate how many revolution. So you need to convert revolution. One revolution means one turn. One circle is 360 or 2 pi. Okay, so this is a new currency after chapter 5. New currency that we'll see in your question. And we'll start to use right-hand rules. Right-hand rules. Okay. Right-hand rules means you follow your tip of your finger. If the motion go this way, the axis will go up. The z-axis will go up. And the angle here you see is anti-clockwise. Clockwise. Okay. This is from the top, view from the top. So now, rigid body, we introduce you two new symbol, alpha and omega. Angular velocity, we call it omega. So how do you calculate velocity? Velocity, you take distance divided, not distance, sorry, position. Or distance also can, position derivative with time. But now you're looking at angular dimension, rigid body. So how do you define position? In this case, you use theta. Okay, so theta. So omega linked with theta. And positive direction anti-clockwise. Right-hand rules. Okay, start applying right-hand rules already. And unit, you start to use radian per second. No longer meter per second. Radian per second. Okay. So once you have a velocity, you can find acceleration. How you define acceleration? You time differentiate your angular velocity. So alpha, also anti-clockwise, both anti-clockwise, positive. So is your dw or d omega over t. This is your angular acceleration. So is a d angular velocity divided by time, d omega dt. So the unit is radian over second square. There are two. You can either differentiate this one more time. It becomes d square. So same, if your acceleration slow down, we call it deceleration, but you need to add the word angular. Angular deceleration. Right. So you have two new equations, and you can combine them to, you freeze the time like what you did in chapter 1. You freeze the time, you rearrange, means this, you move the dt to left hand side, alpha move down, move your dt to left hand side, move omega down. You arrive at alpha dt equal to I think something missing in my equation there. It should be is it something missing? Okay. dt on move. Okay, correct. This one. Okay. So I move the first one to this one, and then this one I substitute the dt. Okay. Then I arrive at one equation. So I have d theta omega dw. You compare this equation and this equation. You're actually changing A into alpha. You change V into omega. Okay? Basically, all you already know already. Just need to change the symbol. V into omega, A into alpha. So, if you have a constant acceleration, you can derive the same. These three equations that I write on the whiteboard here. By substituting the V into omega, A into alpha. You arrive at these three equations. Okay, I'm not going how to derive these three already. If you're interested, you can go. But I won't ask you the derivation steps. It's more on the application of equation. So the first one, you see V equal to VO plus AT. Omega equal to omega O plus alpha T. Change the alpha, change the V into omega, change the A acceleration into alpha. But now you're talking about angular. Okay, the rest is you just modify chapter 1 equation into angular. Now, same diagram, we modify a little bit. We add more parameter for the same diagram that you see. The rest you read. This slide you read. So it just tell you what happened to that point. The rest you read is more on derivation. You know velocity equal to ds over dt. Right? You know that v equal to change of position derivative of time. And what I draw on the whiteboard here, when you look at very small changes on the curvature motion, s equal to r theta, you move this equation into here, s equal to r theta. You know that r is fixed. R is fixed. It's like your brain distance central spinal to your eyes. Same. Right? R fixed. So you pull the R outside and then you change the d theta. Yeah. So when you in angular motion, theta is equivalent to a position. You can look at as position. Your S in chapter 1. Okay. So another new equation that you will always use in your assessment or test 2 or final exam is to find V. Velocity, you change omega and R into velocity. The V you see is in chapter 1. This one is, you can change this one into tangent normal direction. But this one is fixed. Omega is anti-clockwise positive. So now omega R is fixed, but omega direction is important. Direction is anti-clockwise positive. Okay. Again, this is a very popular equation. V equal to omega R. Chapter 5 onward, you will always need to derive this one. Not derive, but use this one to find the V. So in other words, how you know you are looking at chapter 5 or rigid body question? You will no longer see velocity in the question. You will see angular velocity. And then the question will ask you to find velocity. It will ask you to find V. Okay, so if the question you see, oh, this one angular velocity, angular acceleration was given, most of the time you need to convert the angular velocity and acceleration back to the velocity. Okay. The rest you read. And now the equation here is the vector program, vector solution. If you take omega directly multiplied by r, this is called scalar, or we call it speed. Velocity is a vector, but we want to calculate the magnitude of the velocity with speed, right? So here, so also same. So if you want to use vector, you want to calculate the vector, you take omega cross rp. Omega cross rp. Okay. So this hand here is to find the velocity. How you find the velocity direction? You look at the angular velocity. In this case, is this axis. You cross to the r. You cross to the r. Then you find the direction. You look at this. Omega cross, your finger pointing to r. W pointing to r. Yeah. Oh. Cross, this is cross, the omega cross r, rp. Mean the distance of this one. And omega and r always 90 degree here. Always 90 degree here. Okay. I highlight here, omega cross r will not same as r cross omega. It will not same. The direction is opposite. Means chapter 5 onwards, your answer always need to write omega first, then r. If you write r, omega, put question mark. I don't know whether this student understand cross product for this one. Okay, so there are two. The one I write on the top here, this is to find the magnitude. This is vector. One is magnitude, one is vector. The rest still the same. You can split all the vector into tangent and normal direction. This is what you learned in previous chapter. Okay. Previously, how you find acceleration in tangent? You take v dot or v divided d differentiate with time. How you find normal acceleration? V square over rho. This one you learned before. So in this case, angular body, like your spinal cord to your eyes, are same. So you need to change the rho into r. Okay, and you learn what is the velocity when it become angular body, omega r. And then what is the definition of alpha? Or angular acceleration is your velocity differentiate with. Okay. So you rewrite. This one is what you learn in chapter 2 or chapter 1 or chapter 2. You change your v in terms of angular velocity and momentum, angular velocity and acceleration. V equal to omega r. Change this one. V equal to omega r. Then you know r is fixed. You pull the r out. You pull the r out. You d omega dt is actually is angular acceleration alpha. Same with this one. An equal to v square over rho. What is v in angular body? V equal to omega r. So you square it, you get omega square r square. What is rho? Rho is your r. You do your mathematics, cancel the r, cancel. You get omega square r. So new equation today. You can find tangent direction of your acceleration equal to omega r, alpha r. An equal omega square r. This is another equation that you transfer from previous chapter. Okay. This is just a explanation. When the p, the speed or velocity increase, so at will be same as your vt. But if speed decreasing means deceleration. Decreasing means deceleration. Your acceleration will be negative, right? So negative means at will flip to another side. Now positive negative very important already in rigid body. So when you slow down, your at arrows turn to the back already. No long, it's opposite of your tangent direction. All right. So same normal still pointing in. All right. Still pointing in. These are the cross product of acceleration if you derive. So A equal to dv dt, you know that your V equal to omega r. So you do the cross product. How to use this one? Because in vector, alpha equal to dv dt. What is dv dt? Omega r dt. You have two components here. Means you do the du v equal to u dv dt plus v du dt. You use this equation. Okay, this is the cross products. Okay, so you arrive at this one, Arrive this one. I will just go very fast on the derivation. You observe, this one you go home and see. Important is how you apply. Okay. They have more and more equation involved. Yeah, I will throw you all the equation. This one you go home read. You go home read. What is important is the last equation on the screen here. Okay, this equation. So your acceleration now, you have tangent and normal direction. Your tangent direction A, how you calculate? You take alpha cross R. Then your AN is minus omega square R. Normally, student make mistakes, he forgot about the negative here. Yes, straight away use this one. So rigid body a bit different from the particles. Particles is V square over rho and V over T. But when it comes to rigid body, you are using right-hand rules and they always cross product. And the formula will always omega then R. Okay. Magnitude still same, square AT, square AN, square root. Okay. Today will be a lot of theory. So, okay, I'll give you one diagram first. So if you have gear, so gear 1, gear 2, we look at, you see the motion. If gear, this big gear, it rotate here, you're going to push the gear on the right hand side. So the motion actually is a counter direction when you have a gear. So A and A prime, they meet at one point there. And A and A prime, they move in a circular motion, but different direction. So here, if you split into two different free body diagram or two different kinematic diagram, VA will move here, VA will move down also. Then you split into normal and tangent direction, like what you did in the okay. The diagram here, this one is the acceleration. The diagram below here is velocity diagram. Okay. This diagram acceleration is what you learned in previous chapter. At point A, you know that point A is a circular motion, curvilinear motion. This one move down, right? So where is the normal tangent? Normal pointing inside, tangent follow the direction. Then you have two direction, you combine become resultant. This is resultant, right? Same with another side, same also. Because this one rotate this way. Rotate this way, tangent go down, normal go inside. So you have two direction, you combine the vector, become resultant. Okay. Look at this example, then we call it a day. Example 1. You start to see something a bit different from the previous one. Which is you'll see there's a reference point on the object. Previous chapter, you won't see this one. Chapter 4 onward, you'll see 1 point, reference point from a center, and then angle was given, and so on. Okay. So the chord is what arrive a wheel, which is initially at rest. The initial velocity was given. Typo error, this is angle 0. It's not U, it's an angle equals 0. Means this one, this angle. And in this chapter 5, all the positive direction is anti-clockwise. So anti-clockwise, positive go down. It start with 0. If a force is applied to a chord and give it acceleration A, 40 meter per second. Here, you see it gives you as a normal acceleration, but this is a rigid body question. You need to change the A into the one that you see on the screen, right? Angular velocity of the wheel, you need to find angular velocity of the wheel, which is your omega, and angular position of line OP in radian. You need to find the theta. Angular position of OP, this one. So, part A, part A. Part A, angular velocity of the wheel. So you know that point P, when you rotate, point P is having collinear motion. Collinear motion, then you can split into normal and tangent direction. You focus on point P first. Then you look at point P, how point P move. If it move in straight line, then you solve by normal equation. But you move in circular or collinear motion, then you need to split into N and T direction. Okay. So you are given one acceleration value there, or in function 4t. So point P, you know that tangent is always follow the curve, the tangent curve. So you have the acceleration of P on tangent already. Given in the question, which is 4t. Right? And what is tangent direction equation? You learned this now. What is the angular direction? T, alpha r. Okay, so you change on the left-hand side, the normal acceleration in tangent, you change into angular dimension. So angular acceleration equal to alpha r. R was given 0.2. You substitute inside, you get what is your alpha. Your alpha is in one equation. Alpha equal to 20t radian per second square. Anticlockwise. Positive. Okay. Yeah. Now, then after that, you recall what is alpha. Alpha is angular acceleration, where you take angular velocity and time differentiation, omega. You move your dt to left-hand side. You integrate. Then you arrive at one equation. Alpha just now, you find from the previous section. Alpha, you substitute back 20t dt. Because here you don't have t term, you need to refer back where's your t term. Alpha equal to 20t. You integrate this one, you get 10t square. Integrate this one, t square divided by 2. This one becomes 10t square equal to omega. So from this is how you find your alpha and omega. Okay, it's like you drawing your chapter 1 graph. You convert, you recall back what is the definition of velocity and acceleration. Then you look at the question, what you have. If you convert back to velocity, then you integrate. Yeah. Anticlockwise positive. This one, anticlockwise. Okay. Sorry, it's okay. Oh, like this, okay. This question is follow the motion of the rope. It follow the motion of the rope, and it just tell you the direction of the spinning. Okay, tell you the arrow. Here you don't say positive. You don't say. It just tell you the direction of that P. Sorry, I should not mention positive. Okay. So chapter 5, chapter 6 question. At the end, you need to tell how it spin or how it turn. Whether it turn clockwise or anti-clockwise. Then part B, you just derive from the definition also. Part B asks you what is the angular position, means you tell angular position actually is your S. This one. You change the chapter 1 S into theta. You find out which one is missing, then you can use. You can use this derivation or straight away use the equation. Same. So at the end, you integrate, you'll get for 3t or 3 radian. Okay. Example 1 is just a recap of what we learned previously. What is the definition of angular velocity? What is the definition of angular acceleration? Then you flip back and there. Okay. Example 1, this one is fundamental. It's fundamental. You won't see this one in assessment. Okay. Right. So next class we will look at another example. We stop here.